while we are not going to be looking at the electron configurations, one of the things we will be looking at in here is valence electrons. And the valence electrons, these are the electrons in the outermost energy level of an atom. And the reason why we look at the valence electrons is because they are the ones that are involved in chemical bonding. They're the ones that are most involved. We talk about electrons being transferred from one element to another. It's the valence electrons that do that. We talk about electrons being shared between elements. It's the valence electrons that are shared. So, in order to determine valence electrons, this is very simple. What we're going to do is we're going to look at all of the groups here that are labeled with Roman numerals and the letter A. So if we look at all of the main group elements, that is the ones here with the Roman numerals and the letter A, these here are the ones for which we need to determine those valence electrons. And to determine the valence electrons, what we do is we look at the Roman numeral, and that tells us exactly how many valence electrons they have. So for example, we look in group 5A right here, that tells us that these elements in this group have 5 valence electrons. We look in group 3A, that means that these here have 3 valence electrons. And the way that we represent those valence electrons is by using something called Lewis dot formulas, sometimes called Lewis structures or Lewis diagrams, electron dot. Yeah, so here, some things that you should know. What I'm going to do is I'm going to write down a bunch of words. I'm going to put them into columns. And you'd think that chemists have standardized their vocabulary very well, but we haven't, at least in this case. And the reason why I'm creating 3 columns is because there's about 20 words or combinations of words that stand for the same thing. And I apologize in advance for our lack of standardization. So basically what you're going to do is you're going to pick out 1 or 2 words from the first column. You might pick a word from the second column, and you can pick any one of the 4 words in the last column. And they all stand for the same thing. So if I talk about a Lewis dot structure, that's the same thing as a Lewis formula. It's the same thing as the electron dot diagram. It's the same as the Lewis electron dot structure. So again, all of those things, any combination of words from the first column, and we can choose whether or not to include them from the second column, and any word from the fourth, they all stand for the same thing.
Why do you have 2 structures in the third column?
I don't know, because I must have done it wrong. Because I meant to say symbol. How does that sound? Now we have 4 different words. So we can talk about the Lewis symbol, and it would be the same thing. Thank you for noticing that. So here's what the Lewis dot formula is. What it is a chemical symbol, and so I'm just going to use a generic letter X to represent the Lewis symbol. And then we can place around it up to 8 dots. And so this is the maximum number of dots because, if we go back here, the largest number of valence electrons we could have is 8. So we'll never have more than 8 valence electrons, because once we get up to 8, then we start over at a new level. Now when you write out the Lewis dot formulas for an element, what we do is we place 1 dot on each side before we begin doubling up. So we could count 1, 2, 3, 4. So again, here we're placing 1 dot on each side, and then we double up. And there's 5, 6, 7, 8. And as far as which side you double up on, it doesn't matter. And if we only showed 1, it doesn't matter. I could show 1 here on the left-hand side, which would be the same as showing 1 on the right-hand side, which is the same as showing 1 on the top, which is the same as showing 1 on the bottom. So as long as I place 1 dot on the top or bottom, left or right, they all represent the same thing. If I show 2 dots, I could show it like this, or I could show it like this, or this. Any combination, as long as they're not on the same side, represents the same thing. So, again, the dots here represent the valence electrons. And we place one dot on each side before we begin doubling up. And so that's how it would look if there was a total of 8. So if we looked at the Lewis diagram for an element in group 1A, it would be the symbol with one dot. In group 2A, it would be the symbol with 2 dots. Group 3A would be the symbol with 3 dots. Group 4A would be the symbol with 4 dots. Remember, the placement of the dots is not that critical. It's just one dot on each side before we begin doubling up. So the fact that on this one here I put it on the top right and bottom doesn't matter as long as there's 3 dots and they are all on different sides. That's all that really matters. Group 15 would have 5 dots. Group 16 would have 6 dots. Group 17 would have 7 dots. And group 18 would have 8 dots. And then if we wanted to write out the Lewis symbol for an element, let's say that we wanted to write out the Lewis symbol for magnesium. The Lewis symbol for magnesium would be written as Mg. And how many dots would we use? 2 dots. So I could put them on the top on the right like this, or I could put them on the bottom on the right, bottom on the left. They all represent the same thing. So the actual Lewis symbol, we would use the chemical symbol for that element, and then we'd write 2 dots, one on each of the 2 different sides. Now there's all the A groupings, there's one element, and only one element, that does not have the correct number of electrons, valence electrons shown. Anybody know which element that is?
Oh, it wasn't that. We have 6 dots on group 5.
We have 6 groups, 6 dots? Well, darn it. Well, that's just because I made a mistake there. There's 5 dots. So, go back to which element on here would not have the number of valence electrons represented by the group? Only one.
Is it nitrogen?
It is not nitrogen. Nitrogen would have 5 valence electrons. I'll give you a hint. It's in the inert gases.
Helium.
Helium. And why helium?
Because it's already has heat, or because it's already carrying nothing.
Yeah, well, how many electrons does a helium atom have? Just 2. If it has just 2 electrons, there's no way it can have 8 in the outer level. So helium is the one exception. And so when we write helium, its Lewis diagram looks like this. We write it as He, and we actually write the 2 dots on the same side. Any other one that has 2 dots would put them on different sides, but we put them on the same side for helium. And that's because the first energy level holds a maximum of 2 electrons, and since they're both on the same level, they are paired up. And the reason why we represent them like this, 1 dot on each side before we begin doubling up, is because this represents how those electrons are paired up. So in the case of an element in group 5A or 15, this has 5 valence electrons. This shows that we have 2 electrons that are paired up, and then 3 of them here that are unpaired. So it does represent the pairing. In the case of helium, the electrons can only be in the first level, and the first level holds a maximum of 2 electrons, and so they have to be paired up in the case of helium. Otherwise, every other one that we look at in the table would correctly have its Lewis symbol drawn based on how we've written these diagrams. Now let's say we don't know your Roman numerals. What's another way we could tell how many valence electrons it has based on the group numbers written above? In other words, let's say we were talking about group 14. How would we know? What would be an easy way to remember that? Chloe?
Are you talking about the shortcut where we use the noble gases?
No, no. I'm talking about looking at the group number. How can we tell the number of valence electrons? Go ahead.
Either subtract 10 or just use the second digit.
All right, just use the last digit. So in this case, for group 14 would have 4 valence electrons. Group 17 here would have 7 valence electrons. So if you don't know your Roman numerals, that's another way you could do it, is to look at the last digit of that number. Now the other thing here is what about these B groupings? How do we write Lewis diagrams for these? Well, for these, we typically don't write Lewis diagrams. If we did, they would usually have 2 valence electrons, but sometimes 1. So we're not going to worry about them. And again, chemists typically don't write Lewis diagrams for these elements anyhow. So don't worry about the number of valence electrons. You won't be asked in any of your homework about them because we typically do not write Lewis diagrams for the transition elements. Which of these elements here would have a generic Lewis symbol that looks like this? 5, 4, 3, 2, 1. And of course that would be sulfur. That'd be sulfur, because if we go back here, we see that sulfur has 6 valence electrons because it is in group 6A, and this model that we have here does show those 6 valence electrons. All right, that takes care of this stuff here.